Hello, and welcome to this video about point octupoles, also known as ideal octupoles. Octupoles are an arrangement of 8-point charges with equal magnitude on the corners of a cube, so that the net charge is 0, and the dipole moment and quadrupole moments are also 0, and so the octupole moment is left to dominate. This charge structure becomes a point octupole when the sides of this cube tend to 0, or become infinitesimally short, so that there is only an octupole moment from any distance from this structure, which is like a point in space. You can see on the diagram that, like the quadrupole, this structure can be oriented to be aligned with two unit vectors p and q. We'll align them with the x and y axis for now. This octupole moment is filled with symmetries, and another set of p and q vectors can be chosen to describe its orientation in space. Here is an example of another pair of p and q vectors that we can use to describe their alignment. Here are some definitions of quantities used to describe a point octupole. Firstly, there is r, which is the distance of an observer from this point structure. Then there is epsilon, which is equal to one of the sides of this cube. Calling the length epsilon implies that it is going to be limited to 0. Then there is q, which is the charge of each corner of this cube. There are positive and negative versions of this charge on each corner, but the magnitude of each charge is equal to q. Capital Q is the octupole moment of this cubic structure. I looked up octupole moments on the internet to try to find out if there was a standard variable used for this quantity, and the best I could come up with was Q3. So if quadrupole and octupole moments are used together, we could use Q2 and Q3 respectively. Otherwise, I could just use Q when octupole moments are used on their own without any quadrupole moments to confuse them with. It must be noted here that the value of the octupole moment is equal to epsilon cubed times the charge on each corner q. So as epsilon tends to 0, the charge q tends to something extremely large. Theta and phi are the angular positions of the observer with respect to a particular orientation of the octupole moment. These angles are measured against the p and q vectors used to define its orientation. So to get a feeling for what an octupole moment is, we'll calculate one that's not a point, and that has a side length of L and charges Q as shown. And so this is what the octupole moment is for these particular values, in this particular problem. Having a larger cube increases this moment greatly. So now to find the voltages and electric fields induced by a point octupole in space. We'll just make this cubic structure larger so as to better illustrate how to calculate the distances from the center of this structure to the observer, so as to calculate these electrical quantities. This is the distance of point A, also called the observer point, from the first charge labelled 1. It was calculated using the geometry of the diagram and also from Pythagoras' theorem. After a lot of expansion and simplification, we get this expression. Using a similar technique, we can calculate the distances from all 8 charges to this point A. And I'll just write out the equations for all 8 charges. So this is what the voltage is in terms of these charges. Voltage is proportional to the inverse of the distance from any point charge, and these can be added together. because voltage is a scalar and has this property that allows for this. The fraction is negative when the charge is negative. Notice that d4 and d5 are both negative, because they are negative in the cube. Then we'll have to leave both the epsilon squared and cubed terms when we limit epsilon to 0. Notice that we can substitute capital Q in for small q epsilon cubed here. We can't use normal algebra to calculate V because the math is too messy, and we couldn't do it for the point quadrupole, which is much less messy. So we'll use numerical techniques instead. We'll use a computer program to calculate the values of V for varying values of the angle phi, while theta and r are held constant. Then we'll plot these values of V on a graph against phi, and look at the function, and try to guess what it is. We'll do a similar thing for theta and r, plotting V against theta, and then against r. These three functions should multiply together to give us a value of voltage as a function of all these three variables. So this is what V looked like as a function of phi. It looks like it is sine 2 phi multiplied by a constant. We'll try plotting this function next to it, and it looks like it could be exactly equal to it, if only we could find the constant a to make it equal. We'll do that by finding the ratio of any two non-zero points on these curves, and finding the ratio of them. It is better if they are close to the maximum values of the curve. And after we found it, the function was nearly exact, being out by only a small number, like 10 to the minus 5. Then the next variable we'll check V for is the distance of the observer from the octupole, which is r. V is proportional to r to the power of minus 4, so we can plot the fourth root of V against r to check that this proportion is correct, which it is, since this equation gives us a straight line. So all that's left to do is to plot another equation of r to the minus 4 to check this. We'll do that by finding the ratio of any two non-zero points on these curves. It looks like it could be nearly exactly equal if we could only find the correct constant a. And after finding this constant, we find that this equation is correct, but slightly inaccurate for values closer to the point octupole, which would be expected. Lastly, we have to find what V is as a function of the angle theta, which gives us this curve which can't be guessed by sight. So we'll have to use a fast Fourier transform to find what it could be, assuming that it is the sum of sines and cosines of different integer multiples of theta. After using this transform, we find that V is this function of theta. Then we have to compare this function with the values of V that we measured, and it looks like it could be correct, but we have to find the correct value of A to make it match. And after we found this value of A, it has a perfect enough match to say that this is what the function is. So now to discuss how we use the fast Fourier transform to find this function. We'll assume that the function is of this form, and in this case that n is not too large. We can start with n is equal to 10, and then try n is equal to 3 after we've found the function, so as to more accurately verify it. So this is how we build the fast Fourier transform matrix to solve this function. We have to find two n plus 1 values of theta and of the voltage to solve for these coefficients. the values of theta would be made equal to equidistant values going from 0 to 2 pi, and these would be the values of theta calculated for when n is equal to 4. Now we can multiply all these three functions together so as to get v as a function of these three spherical variables, r, theta and phi. We only need to find the value of a to complete it. Notice that this requires a high degree of precision, so I used special high precision numbers to find it. Since I used JavaScript to do all these calculations, I used math.js to give me access to a number type called big numbers, which could give me a precision of more than 64 significant figures, which I needed so as to find this constant. I also needed to use the local maxima of v so as to give me larger numbers to work with in the calculations, so as to improve their accuracy. A local maximum of v for phi occurs when phi is equal to pi on 4. I had to use some calculus to find the local maximum of v for theta, which I've shown here to a high degree of accuracy. And so I found this value of a, and I got it to 16 decimal places. So this is what the voltage was equal to as a function of these variables. I checked it for a large spread of these variables, so it could be proven to be correct to a high degree of accuracy. Now to find the electric field as a function of these variables using vector calculus. E is equal to the gradient of v multiplied by -1. Then we'll substitute this function in for v. We'll then expand the gradient out for spherical coordinates. We'll do each part separately. First, we'll get the value of E in the direction r, which is facing away from the point octupole. We'll factor out the functions of theta and phi, which are like constant terms for this partial derivative. Then we'll find the partial derivative of the remainder of this function, which is equal to this. So this is the r component of the electric field induced by the point octupole. Next, we'll find the theta component of the electric field from this partial differential equation. We can factor out all of the terms which are not functions of theta and look like constant terms to this partial derivative function. Then we'll find the partial derivative of the remainder of this function. And after simplifying this expression, we get this component of the electric field. Lastly, we have to find this phi component of the electric field from this partial differential equation. We then factor out all of the terms that are like constants for this equation. Then we partially differentiate the remainder of this equation. We then use some trigonometry to transform this part of the equation into this, and then we can cancel out these sine terms. We can then use trigonometry again to transform this part of the equation. After simplifying this equation, we get this last component of the electric field. So this is the final equation for the electric field, which can give us its magnitude and direction. And this equation can have all of the common terms factored out to give us this. Now to have a more detailed look at how we manipulated the trigonometric equations that we did to find E phi. This was the first of these equations, and we have to manipulate it so that a sine term occurs in it, which we can divide by the sine in the denominator. This is the expression that we have to substitute in for cosine 3 theta. So then we substitute this term in to get this. and we get this expression after simplifying the last expression. Then we factor out this term, and this term in brackets is equal to sine squared theta, which gives us a sine term in the numerator to cancel out the sine term in the denominator. This is the other expression which needs simplification. We can factor out a 2, which gives us this term. And so this term transforms into this, being a very common trigonometric identity. Now to test this equation to see if it is correct by comparing it to the value of E generated by numerical methods. These are the x, y and z components of E found by geometry from the diagram that we use to find the voltage, and it is found in a similar way to the voltage. Splitting these values up into these components allows us to add them. These are the components of the electric field in spherical coordinates, so that we can compare the function we found from vector calculus with the function found by numerical methods, and after testing it I found that they were equal to a high degree of accuracy. So now to use the equation that we found to find the electric field for these given values. This is the equation that we've found and that we'll use. We only need the r component of this equation, so we'll only use this part. Substituting all of the values into it gives us this expression, and solving these parts of the equation gives us this expression. And we finally get this as the value of the electric field, which is pointing inwards because it is negative and is possibly spiraling inwards. So I hope that you have learnt a lot about electromagnetic theory from this video, and also learnt new ways to solve complex problems. Thank you for watching this video, and please click on the subscribe button to see more of the videos that I'm producing.